Good morning, ladies and gentlemen. My name is Tomas Tamulevičius from Kaunas University and Technology, and I was asked to introduce our first invited speaker in the Open Readings Conference. So it is our pleasure to have Professor Ursula Wurstbauer from Münster. And start our early morning by waking us up with an interesting and exciting topic, 2D quantum materials on demand, twisting, stacking, and defect engineering. So please welcome and start your presentation.
Okay, so first of all, thank you very much for the introduction and for giving me the opportunity to talk here. So maybe if I could get the allowance to share my screen, then maybe I can, present a few slides. Okay, perfect. Thank you very much. And okay, let me try it again. Yeah, no, it should work, right? Yeah, okay, perfect. Sorry for this delay. And now we are set. So good morning, everyone. Also from my side, welcome to today's talk. And first of all, I would like to get started with this picture. So meaning typically on the first slide, I would present you a picture of the nice city center, the old city center of Münster, but in this time, so that's a night view of our medical center to express, our thoughts to the people in Ukraine, to demonstrate that we are standing with them. And with that, I also would like to encourage you, not only, in general, don't stop talking to each other, be interested, be open-minded. And I guess science is really an excellent, platform among all people over the world to communicate, to stay in contact, that such things don't happen. But with that, now let's talk about 2D quantum materials on demand. So actually, before I get started, let me thank the group. So here this picture, we had the pleasure in the summer that we could stay somehow together, even with COVID. Of course, at the moment, it's a bit more difficult. It's, I guess, also the reason why we talk to each other over this virtual platform, but I would like to thank them. I will present today not only their work, but also a lot of work of other, let's say, colleagues. Nevertheless, they are really doing a great job. So about quantum materials. So meaning, first of all, let us think about what are quantum materials for. So meaning we have this 4 big parts in this term of quantum technology. So we have quantum information technology, we have quantum cryptography, quantum sensing, and of course, quantum computation. And I guess you all are aware that we have the first quantum computers really set up. So one, for instance, by IBM, the System 1. And if you have the chance, that what is at an exhibit where they, show us the quantum computer, and actually everything what you see here is just a fridge, to provide low temperatures. So actually the quantum computer, it sits really here at the cold thing at the very bottom. And that's exactly, the materials, what we are talking about, not only for quantum computation, but in general, for this big theme, quantum science and technology. And that's exactly what we would like to talk about today. And with that, that's my outline. So I would like to first think about what is a quantum material, because actually the definition is not so clear. Then, of course, talk about 2-dimensional quantum materials. They're really fascinating in my opinion. And then, of course, on demand, so meaning what does mean 2D quantum materials on demand. So with that, let's get started with the first topic, quantum materials. Well, classically, as you know, each particle can be seen as an individual entity. In quantum matter, we have the Heisenberg's uncertainty principle. So with that, it's difficult to tell individual particles apart, meaning typically behavior can be described collectively, but also, we have really distinct, quantum properties attached to an entity, to a particle. And if you are, would like to know about quantum materials, I don't know what you do, but however, for me, it's something like, okay, let's give Wikipedia a chance to see what's going on. And then in terms of quantum material, actually, it's maybe not that, let's say, conclusive, because what to learn is quantum materials is an umbrella in terms of condensed matter physics that encompasses all materials whose essential properties cannot be described in terms of semi-classical particles and low-level quantum mechanics. These are materials that present strong correlations or some type of electronic order, such as superconducting or magnetic orders, or materials whose electronic properties are linked to non-generic quantum effects, like topological insulators, direct electron systems, such as graphene, as well as a system whose collective properties are governed by genuinely quantum behavior, such as ultra-cold atoms, cold excitons, polarities, and so forth. You see, the definition, it's more or less everything and nothing, I would say. It's really a whole bunch of different materials and properties. So also here for me, that's what a little bit, first and disappointing to see, there's no real definition. And even, here later on from a statement from a paper in Nature Physics, they say, on a trivial level, all materials exist thanks to the law of quantum mechanics, and there are cynics who will privately wonder if the description isn't too broad and well catchy for its own good. Maybe, that's a little bit typically in science. You try to be at the forefront and to have some big buzzwords, and the rise of quantum materials, as seen in the editorial of a Nature journal, of course, is something in, everyone's, let's say, would like to somehow be part of it. On the other hand side, I believe, we find in this definition already some good ideas of what is a quantum material, because basically, of course, from your quantum mechanics course, you need to describe the quantum mechanics to describe the properties and to describe, fundamental physics or physics at all, if you go beyond the pure classical directions. However, there are really something like electron correlations, superconducting. So, there's already some hints, even if it's maybe not very well defined. Instead, let us think a bit closer of what is really needed to have a quantum material. First of all, there are interaction-driven phenomena, so intertwined degree of freedoms. What are degree of freedoms? So charge, spin, orbital, lattice, topology. And, if you think about the quasi-particle zoo in solid state materials, and here I just have a few examples. Already the band electrons and holes are quasi-particles. Why? Because they live in the solid state matrix, and we attach an effective mass to them. And due to this effective mass, we, touch the interactions of this electronic state to all the atoms, 1,000 atoms around, to one entity, the mass. That's the interaction to the solid, the surrounding, the potential of the solid. We attach spin traits, meaning with that also even, the electron and holes in a solid state are something like quasi-particles. We have, bound quasi-particles like exciton and Coulomb-bound electron-hole pair. We will see Cooper pairs. There are also other prototypicals like phonons, and all of them can interact. So meaning a phonon can interact with an electron. And phonon can interact with an exciton even if this is already a bound particle. And these interactions can, of course, initiate different behaviors, as you know. There's a second direction what you should think of, the non-generic quantum effects in states, such as excitons, and exciton can emit light, and that's a typical photon, and single photon is a typical two-level quantum system, which is very well defined, which is needed, for instance, for quantum information systems or also quantum cryptography. We have so meaning for the photon, what is well defined is the polarization properties, typically, expressed by the Bloch sphere here. This, spin up, spin down, or let's say polarization up, down, or anything in between, which can be well addressed. And, and last part, which is often attached to quantum materials, is the so-called emergent behavior, which causes phase transitions to a new behavior like magnetism, like superconductivity, mud insulators, Bose-Einstein condensation. So these are big words, and I guess before I already start here at the very beginning to lose some of you, let me first introduce emergency. What is meant with emergent behavior, because it's nothing specific for physics or for quantum materials. So emergence occurs when an entity is observed to have properties its parts do not have on their own. Properties or behavior can emerge only when the parts interact in a wider whole range. And there is, different directions from science, philosophy, sociology, system theory, art. I mean, there are many, many directions which really dealing with this concept of emergence. And with that, let us give a few examples. So for instance, this nice ice, let's say, flowers are already, they are formed by dipole-dipole interactions. So meaning the peculiarity of the hydrogen bonding provides us with this nice pattern, the pattern formation. Also, the typical pattern, maybe you know from the beach, the sand, which is formed by the combination of laminar wind or water flow, which is very unique, but it's also already a collective behavior, which provides then this emergent phenomenon. Cooperative motion would be another example, like riding a bicycle. You need to learn how to do it, and then you can use it to drive a bicycle. In maybe go a little bit beyond in sociology, it's there are a few definitions, but I guess it also express what's meant with that. The relative unorganized patterns of social interaction in human groups, or describes how people behave when they're united by a single short-term goal, or the spontaneous behavior of a group of people responding to similar stimuli. And what is meant with that? Well, for instance, that's an example, the typical roller wave in a soccer stadium. It's really an collective behavior. First of all, again, you have interacting a lot of people or interactions. You have collective behavior, so it's somehow synchronized. You can even say it's a coherent motion, because otherwise you wouldn't have this wave type circling around, the seats. And with that, you have a new form of motion, and that's the emergent behavior which occurs. Well, swarming, birds, fishes, it's also the same. It's also an emergent behavior. People communicating to each other in this way, maybe it's not a direct communication, it's an indirect communication. Maybe the social distancing, this would also work. So also, that's somehow and can also occur to somehow an interaction. And if the interaction is strong enough, the behavior can change. But now, how does this, help us to go back to the physics? How does this help us to guide us to some question in quantum physics? So meaning, when it's sufficient to describe single particles, I mean the behavior of individuals like this, and when do we need to go to many body properties? So meaning, for instance, like the people here doing this roller wave. What's the impact of collective behavior? And then how do we quantify interaction-driven quantum phase transitions, which provides us with emergent quantum systems? So one, very prominent example is the superconductivity. So here we have defined quasiparticles. The quasiparticles are composite bosons, as we had before. What is it? I mean, the quasiparticles are electrons which are glued together over lattice vibrations over phonons. So that's sketched here. So we have the incoming or one electron with a momentum P1 and second electron with momentum P2. They interact to each other via exchange of virtual phonons. And with that, they go out in this way and this way. And, there's this Polaron picture according to the BCS theory, so the Bardeen-Cooper-Schriever theory. And what does it mean? So meaning an electron interacts with the lattice, which has some polar nature, in such a way by the Fröhlich electron-phonon interaction that the lattice is slightly distorted. And with that, the background has a positive charge because the atoms are a little bit displaced. And with that, a second electron coming by sees there's a positive charge and feels attraction. It's a Coulomb attraction. And with that, these two electrons are bound to each other. At the same time, this electron feels, of course, the same phenomenon on this side. There's a distortion of the lattice, somehow a cloud of positive charge. Of course, there's not an individual, let's say, charge attached to an atom. It's a cloud and field that the electrons are feeding, and with that you have this combination, and with that we have two fermions, two electrons bound together, driving the superconductivity. So with that, I should now go a little beyond, because now let's think a little bit on quasi-particle statistics, because I mixed up now a little bit with fermions, bosons, composite boson. What does it mean? So let's give a reminder about quasi-particle statistics. So fermions are spin-half particles. Here we have the Pauli principle. From the statistic, the maximum value is 1. And if you go to the high temperature limit, we convert to the Boltzmann distribution, the same as for bosons. However, the Pauli principle is important. So meaning if we bring the system down, and system of many fermions down to the ground state, it does mean they need to be distinguished in their quantum states. I mean, every, let's say, or every state can only be occupied by one fermion. For instance, spin up, spin down, the next side, next side, next side. This is very different to bosons. So bosons, the statistic has an unlimited value. For low temperatures, all bosons are allowed to occupy the same state, the same ground state. And also here, we have this link here for high temperatures. They converge into the Boltzmann distribution. So actually, bosons, can we make out of a fermion a boson? And the short answer is yes, we can, by combining them. For instance, if we have an exciton, an electron and a hole bound together by Coulomb interaction, it's two spin-half particles. With that, it's in combination, it's a spin-1 particle, and with that, it's a so-called composite boson. And the same is true for the Cooper pairs. If we have an electron, another electron, as we had it in the example before, glued together with by exchanging the virtual phonon. Also here we have one spin-half particle, another spin-half particle glued together, and with that we have a spin-1 particle, which belongs to the boson statistics. And with that, now we can understand the phenomenon of superconductivity. It's, so to say, a Bose-Einstein condensation. And here I found a nice, let's say, video from Quantum Made Simple, and I hope it works now. Yes, it works, demonstrating what is a Bose-Einstein condensate and what occurs. So at high temperatures, you have many, many bosons, moving around, occupying different energy states statistically, according to their distribution function. And then if, we start to cool down the system, the energy is lowered. With that, the bosons occupy lower states. At some point, we also need to think about the wave properties of the particles. So we can define the material wave, the Broglie wave, and if the Broglie wavelength has the same size as the interparticle distance, they really start to, let's say, be connected, to really interact with each other, such that at some point they have, so much overlap that they condense and then common ground state, this one coherent ground state function, which is called Bose-Einstein condensate. And that exactly occurs for a superconductor. And of course, not only for a superconductor, we know also Bose-Einstein condensation, or that's even more prominent. And that's really called Bose-Einstein condensation. Sorry to a little confuse this, for atoms. But also there are Bose-Einstein condensation work for excitons. So also here we see this transition. So meaning that's, how we can make out of an individual particle, which is a fermion, by interaction via Coulomb coupling, via exchange of phonons. So meaning we have this interaction, which is important. And then if we somehow cool the system down, we change the quasi-particle statistics. And with that, we now can really create a system which condenses, for instance, to an condensate, to an Bose-Einstein condensate with completely different properties. And now the question is, why in this, aspects are 2D quantum materials fascinating, and at least to me. Well, I would like to provide you here for the motivation and citation of Richard Feynman. What could we do with layered structures with just the right layers? What would the properties of materials be if we could truly arrange the atoms the way we want them? And you can imagine, if we have freedom purely two-dimensional crystal, we are very close to this statement of Richard Feynman, because then we can already start to really adjust and tune the energetics of the system, to tune interactions, and with that to exactly stimuli and drive systems into this kind of generic quantum systems, to collective behavior, to emergent phenomena, just by have this interplay of energetics, of quasiparticle statistics, of interactions, and such, if we do everything right and provide the right environment and stimuli, then we can drive this kind of phase transitions and get new phases of matter, create quantum materials on purpose, and for the applications, be able to control them, to tailor them. That's exactly the important part here. And with that, let me ask you a simple question. What do we see here? Now it's a bit difficult in this virtual environment, but maybe think about what could this be connected to let's say 2D materials. Well, actually I provide an answer. So meaning that's just a trace with a pencil. So meaning everyone who is making notes with a pencil is already working with 2D materials. Of course, the graphite, the parental of the 2D materials, graphene, is on van der Waals layered materials, and every time you put some force, some shear force to it, you will, separate these individual layers, as done here. So if I zoom a little bit in here, you see this kind of layered structure. These little sheets here are nothing else than somehow stacked, combined graphene sheets. So what is graphene? Graphene is an hexagonally arranged lattice of carbon atoms. It's atomically flat. It's really one atom thick, close to, or exactly that what Richard Feynman, wanted to have. And, it can be easily prepared by this, shearing off from parental van der Waals materials. And van der Waals material, therefore, because we have strong covalent bond in the plane, however, between different layers, we have weak van der Waals interaction. On the left-hand side, this is a microscope image of a typical in False color representation of such a 2D materials, where you see the different number of layers, how it, it's created by just this typical exfoliation technique. And the typical exfoliation technique is rather that simple as it, you think about. You have a tape with bulk crystal, you take somehow a substrate, in our case, it's a stamping material and a viscoelastic material, where you just, transfer it, peel it off. Then you search for, the flakes you would like to have. Then you can even transfer it to a target substrate. And with that, you are ready to go. And I guess that is really the very, let's say, the great success of graphene, which was, the starting material for this new class of two-dimensional materials. So it was awarded, so André Geim and Konstantin Novoselov were awarded the Nobel Prize in 2010 for the groundbreaking experiments regarding the two-dimensional material graphene. Everything started in 2004, where they published that graphene, can be inserted in a transistor, in a field effect transistor circuitry, that you can measure the transport properties, independence of the of a gate voltage of an electric field, where you see this ambipolar behavior. And with that, somehow the field was kicked off. And you see only 4 years from the first publication to the Nobel Prize, it's really extremely fast. And I guess it gives us an idea how fascinating, how prominent this field is. Actually, what does this here mean? So actually every Nobel laureate donate something related to his or her work to the Nobel Museum in Stockholm. And actually this is what André Geim donated. So sticky tape, and natural graphite crystal, and these little chips, these little devices, which was made with these two, ingredients, where he did all this nice study. So what is so cool and so fascinating about graphene? Well, first of all, the band structure. So if you have a look on the band structure, which can be, calculated like in a textbook, because actually the simplicity to have, the same atoms in the lattice, where we have an sp2 hybridization, and with that we just need to take into account the pi bonds, the pi states, which are creating the band structure because of the overlap. And if you do the mass, you're ending up with this energy dispersion. So we have this at the middle of the Brunel zone, which is also hexagonally. We have this huge band gap. We have this kind of saddle points here in the middle of the endpoint connecting the two corners, K and K prime. And if you zoom in on the corners, we have this linear dispersion. First of all, it's a linear dispersion. It means those particles behave relativistically. They have a reduced speed of light, but rather fast. We need to explain or to describe them with the Dirac equation rather than with the Schrödinger equation. We see some really fascinating relativistic phenomena, typically only visible in high energy physics. So meaning here we have the so-called Klein paradoxon. So meaning that those electrons does not, see a barrier because of the high kinetic energy. And also we have here a touching point. So meaning the occupied states, the valence band states are touched to the conduction band states by one joint state here, but with that you can continuously tune from hole to charge conductivity. Well, there are a lot more fascinating properties for graphene, like it's a strictly two-dimensional atomic crystal. We have the strong interlayer bonds, which are covalent, weak interlayer binding by van der Waals force. It's very thin, very strong, flexible, robust, and inert. And actually, sorry, this sketch here is a demonstration how strong the material is, because if you scale it up and say, well, you have a graphene sheet of the size of this paper here, holded by two people, the sheet would sustain the weight of an elephant, just on the tip of a pencil, which is, I would say, quite amazing. Due to the relativistic charge carriers, we have a record high charge carrier mobility, and actually this comes because the electrons don't interact with the potential of the lattice, they even don't see it. So that's the reason why they move more or less relativistically through the crystal, because for them the crystal feels like vacuum. The material is highly tunable. You can think about various applications in different fields. We have this relativistic charge carriers, with that we get exciting quantum phenomena. And also we can get new functionalities by stacking, by van der Waals assembly, by nanoscopic design. So meaning, think about stacking, and van der Waals assembly will come back later on. So for the moment, I would also give you an idea about the limitations of graphene. So graphene is cool, as we just have seen it. However, there was, at the first years, always the belief it can replace silicon. And why is this not really true? Why graphene cannot replace silicon, for at least not for the big, applications as a field effect transistor for logic devices, is because graphene does not have a band gap. So if you create, or would you like to build a field effect transistor, it's always important that you can reliably turn it off. Turning it off means you have the Fermi level in the band gap with an electric field, with the gate voltage, you tune the Fermi level such that it somehow lies in the band gap where you don't have a loud state. And with that, the resistivity of the structure goes high. There's no current flowing, or almost no. And as soon as you tune the Fermi level into one of these bands, conduction band or valence band, you get again, a high conductivity. And actually, if you see graphene, there is no band gap, so with that you cannot really turn off such a device. And you can make an analogon to a leaky water outlet. So meaning there is always, charge carriers dropping through and circuitry of graphene. And that's a little bit the difficulty for graphene here. Is graphene the only two-dimensional material? No. So meaning, we know quasi-two-dimensional materials created by quantum confinement. So since years, for instance, doped quantum wave structures were also, phenomena like the fractional quantum Hall effect, the quantum Hall effect were studied, and also, the phenomenon were awarded, or the researchers were awarded for the discovery of those phenomenon with Nobel Prizes. Also here, we got already a lot of excitement with quasi-two-dimensional charge carrier systems. However, now we have the ultimate limit of the 2D crystals, and there are many more. So there's really now a whole bench and library of 2D materials. And just to give you a little bit an overview, so the graphene family of the carbon atoms we had just, then we have insulators where we replace graphene by boron and nitrogen. They're metal chalcogenides, mostly doing semiconductors. You have black phosphorus with a slightly different lattice structure, a little bit distorted. And here we have an implant anisotropy. It's also in semiconductor for this black phosphorus. We have layered perovskites. Most of them are semiconductors, very interesting, for instance, for solar energy conversion applications. Then we have two-dimensional magnets like iodide chloride or chromium sulfide bromide. We have two-dimensional metal organic frameworks, covalent organic frameworks, polymers, moving more towards the chemistry direction with various properties, highly tunable. There's a new class of so-called half van der Waals materials, 2D polymetals, where we have atomically thin metal films confined within silicon carbide and graphene. There are topologically insulators. Typically, those are also metal chalcogenides in this structure. And we have also semiconducting and superconducting transition metal dichalcogenides. So you see here, for instance, we have not a pure atomically thin crystal structure. So here we have a triple layer, smallest unit. So meaning here we have some out of plane bonding, but still, you know, it's really less than 1 nanometer thick. And with that, I would say it's still van der Waals or a two-dimensional crystal, because also the next layer would be bonded by pure van der Waals materials. Well, now, if you're excited and you think and wonder, could I try it also myself at home? I would say, yes, you need a microscope. And then you could go, for instance, to supply this kind of value packages where you get substrates, sticky tape, and crystals, you know, already in a package. There are many to try it with some sources where you get those crystals. Is it a new class of materials, or is it already known? And actually, as often search literature go back, there's a nice review article by Wilson and Joffre from 1969, where they discussed the properties of hundreds, or let's say 60 transition metal dichalcogenides. 2/3 of these assume layered structure. And crystals of such materials can be cleaved down to less than 1,000 angstroms. So meaning it's already well researched, the parental materials, however, not to the monolayer limit. And that's, you know, somehow the new direction. But still, you know, for some properties, it's still, you know, worth to have a look on this, let's say, old literature, because a lot of it was already known, and we do not need to invent the wheel, you know, quite newly. So we can, of course, go back and see what is already known on those materials. Well, actually, it's not only known for the electronic and optical properties. Those materials typically are also known as dry lubricants, so meaning maybe in the morning if you ride a bicycle, and then typically you will have a compound where you have some of those van der Waals materials, either molybdenum disulfide as a transition metal dichalcogenide, a natural one occurring, or graphite, graphene, where you have inside, because, you know, of this, the layers smear off, and instead they have perfect, you know, it's a perfect dry grease in that sense. However, let's now go back to the optical and electronic properties. So I mentioned in 2004, graphene was invented, and this the field of 2D materials got another, let's say, kickoff on a new, let's say, bunch, a momentum in 2010, where the group at Columbia by Tony Hines, first of Kin Fermat, you know, identified we have an atomically thin direct gap semiconductor. There was another publication coming up almost at the same time in this direction by another group, and they started exactly this molybdenum disulfide and transition metal dichalcogenide, where we have also an hexagonal arrangement of a metal, it's molybdenum, and then chalcogen sulfur in this sense. And the side view is exactly as mentioned before, this way that we have a slightly out of plane, let's say, bonding. So the two chalcogenes are lying on top of each other. But what is now new, the following. So if they investigated the photoluminescence properties, so the shining light in it, and look what's, you know, how the system emits light. And then they identified the following. If they do it here, it's the energy versus the intensity plotted. For the monolayer in red, I saw a strong signal, and on a linear scale for the bilayer, it looks dark. And if, you know, they now look for the quantum yields, meaning the intensity here as a number of layers. And now the quantum yield is plotted in a logarithmic representation. And then you see really, so the monolayer is bright and then it really goes down dramatically. And it can be explained that due to the stacking, due to the change of the number of layers, you change the properties of the material such that you change from a direct gap semiconductor to an indirect gap semiconductor, fundamentally changing the properties. It's a combination of confinement and hybridization which goes on here. So meaning we have highly tunable materials now. What is so peculiar about the optical properties? So let me briefly explain an absorbance spectrum for this material. So it's a monolayer of these materials. So you see some peak structures here around 2 electron volts, so in the visible range, which is really increased to the 3 electron range, and also, some peaks that's higher. So what does it mean? So first of all, think about, we have a monolayer less than 1 nanometer, and it can absorb up to 15% of the visible light. Oh yeah, which is quite amazing. Also to think in terms of applications, solar energy conversion, for instance, would be one topic. This peaks means these resonances are coming from so-called excitonic absorption features. An exciton, just to remind you, is an electron hole pair coupled by Coulomb interaction, and of course having some electric field which is screened by the environment. And what is quite peculiar here for these materials and why we see the strong resonances, so we have an exciton binding energy which is almost half an eV, or up to half an electron volt, which is really huge. Just the binding of this electron hole pair. And maybe first of all, let me explain you why we have this high binding energy and why it's so interesting for the material. So let's go back to a textbook picture. Now we have the single particle picture. We have the conduction band in a parabolic approximation. We have the valence band, and here we have the band gap. So without an exciton, you would expect if I shining light on it, it will create a hole or will promote an electron from the valence band to the conduction band, leave a hole behind. They will somehow thermalize here to the maximum and minimum, and will then recombine. And with that, the recombined light will have the gap energy. If we have this excitonic signatures on top, so meaning if we have a binding energy and internal energy attached to it, then we have, it appears as if there would be some in-gap states which are not there. It's not a real state, it's, let's say, a virtual concept, because this energy from the single particle states is reduced by the exciton binding energy. So meaning in optical emission, we just have, or also absorption, we see this optical, let's say, energy here, which is the band gap reduced by the binding energy. So in general, if we have this electron hole pair, it can be well described by a hydrogen model. The proton is the electron circulating around, however, of course, with different masses, which we need to consider here. Nevertheless, we can do the same physics. We also get discrete eigenenergy states, the so-called triplex series, so meaning the ground state, first excited, second excited state, until we reach the single particle continuum, which would correspond to the unbound state. And due to the screening of the electric field, this energy of the exciton is proportional to the 1 over the dielectric, the square of the dielectric environment. And with that, the dielectric environment, is important. And if you now think about a 2D material, the dielectric environment is highly tunable because of the this material is so thin. You can have an insulator, then screening is drastically reduced, and with that we have a high binding energy. If you would have a metal in the surrounding, you can do it, just by preparing it like that. Then the screening would be drastically enhanced, and with that binding energy dramatically reduced. So meaning here we have really access to this, energetics of this composite boson. And remind, composite boson is an exciton. It's important if you think about changing the quasiparticle statistics. Something else I should mention, just because of the dimensionality here, the Rydberg series is a little bit altered. So with that, we get already an enhancement of the binding energy by a factor of 4 just by the dimensionality, just to give you an idea. So overall, due to this fact that these 2D materials, are sensitive to the environment, or that they can be exposed to the environment, and that the dielectric environment can be changed. We have a lot of different things that can be, let's say, tuned. We can tune the single particle properties, the energetics, which, just shown here. If you have the 2D materials on a metal, you can change the energetics by enhancing the coupling to the metal. Or just for sensing, if you have, for instance, water molecules on top. We can effectively adjust the far field, the light outcoupling properties. So meaning what is plotted here, you see here that a 2D material, which is on a glass substrate, and that's the far field emission pattern to the air interface, and that's to the glass interface. It's the same emitter, so meaning the intrinsic properties are really the same. It's just, how much light you can guide out. And you can imagine if you have a high aperture optics here, you can couple much more light to the glass side than to the air side. And also here we have the tunability because it's extremely thin. Another example, which provides us with the fact that we can see those materials, under the optical microscope being so thin. So it's the so-called interference contrast, or in reflection and multi-layer system, where we have this multi-interference or let's say reflectance at these interfaces, and such that we can have here constructive and destructive interference depending really on the thickness and the materials in the surrounding. And with that, we can have substrate where we can see those materials as this on this example, or where the materials are completely invisible. And of course, the excitonic properties can be changed as well. So with that, we have now really the flexible, tunable, and universally integratable 2D materials. And now let's see on demand. So here we have, I would like to give you two examples. One, single photons on demand. And why do we need single photons? Well, it's a generic two-level source from two-level quantum states, which is required for quantum information technologies and cryptography, quantum cryptography. And let's first think what is required here. So meaning we need to have quantum indistinguishabilities, meaning, every photon needs to be the same. And from that point of view, since the exciton is the source of the photon, they need to be the same. We need to have a high efficiency because otherwise it will not work for applications. And the photon statistics is important. So what does it mean? So meaning we always need one photon at a time. If you really would like to have one photon with some very specific quantum properties, quantum state, we always would like to have one at a time. And that's defined by the so-called second order correlation function. It's the intensity correlation function. So what does it mean? Let me show you that the measurement is done by the Henry-Brown-Twiss measurement. So we have here an emitter in our 2D material, and photon is emitted. And if we have here a beam slitter, 50-50, since we have a photon and particle, it can either go this way or it can go that way. We have always a single photon detector on both sides. And between those two, let's say, detectors. So meaning if there's a photon coming on, there's a click, and the time is running until there's let's say, also a click, an event on the second detector. And with that, if we have just one at a time, we will have a 0 time delay. We will have a dip because there can be just one photon at one detector. And that's exactly in a continuous wave experiments where we have a different delay time. We have, ideally 0. Due to the background and some uncertainty, it's such that we typically say we have a single photon event below 0.5. Or in pulse excitation, it would mean, depending on the pulse duration or the frequency of the pulse, so the duration, the frequency would have also this kind of peaks, and the 0 peak would be missing. Now the question is, how can we create them on demand? So there was some excitement in 2015, by these 5 papers almost at the same time, in the same issue of Nature Nanotechnology, demonstrating we have quantum light, so a single quantum emitter in this atomically thin semiconductors. And then there was not clear where it's coming from, and now people learned how to induce them, how to control them on purpose, and it's can be done by strain and most likely by natural defects. So it's a combination of both. It's still work in progress, not fully understood where those emitters are coming from. However, if you create these little pillars and displace a 2D material on top, you will create some strain around these pillars. And then you see now for 1, 2, 3, 4 different materials, tungsten diselenide, tungsten disulfide, molybdenum diselenide, and gallium selenide, that you have these little peaks here. This peak, this peak, this peak, this peak, this one here. And those peaks are all single photon emitters. So now they can be somehow placed. However, the energy cannot be well controlled. So that's a little bit an issue, but you know, that's engineering. So we are working towards that direction to become better here. There's another material which is also promising, is hexagonal boron nitride. The natural defects can also serve as quantum emitters, still different energies. However, the advantage here is that it's at room temperature. All those are at low temperatures, at cryogenic temperatures. And there's another concept which can be pursued, because here the defect is playing the role. And why not using the defect on purpose to generate quantum emitters? And it can be done by a focused helium ion beam irradiation of this transition metal dichalcogenides. So the concept is we take a helium ion beam to generate zero-dimensional defects in a 2D material, which can act as a single photon emitter. Due to this focused beam, which is much less than 1 nanometer, you can get high lateral precision, about something like 8 nanometers, because you generate secondary electrons by this bombardment. However, 8 nanometers are still quite good. And in Z direction, the precision is the thickness of the material, 0.7 nanometer. So meaning it's really high. And since it's in defect state, it's a monotypical emission. So you can also check here, it's that's the peak, it's ultra narrow at low temperatures. And then you can measure the autocorrelation function, it's done here. So you see this nice dip, it goes well below 0.5. So from that point of view, check the box. Now we have on purpose a quantum emitter, and it can even be controlled by electric field, because if you insert this 2D material hosting the quantum emitter in a field effect device, such that you can inject or drain electrons through the layer, you can occupy this defect state in an electron, and then you can darken it. So with that, you can see here by electric, let's say, field by voltage to the gate, you can turn this single photon emitter on and off. So meaning it's really a controllable single photon emitter. And now if I get another, let's say 2-3 minutes, I can also, give you another fascination to these 2D materials. It's not only that we can generate these quantum emitters on demand, but we can also play with the twisting and stacking. And that's really a rather new field where a lot of excitement is put in as well, and where we are really very close to rigid Feynman's, there's plenty of room at the bottom, idea. And here now we use the properties that we can combine these van der Waals materials on demand, because we don't have an out-of-plane covalent or ionic bonding. With that, the registry, like in the LEGO here, is missing. So I mean, it's not such that we just can stack together what fits together. No, we can, with the van der Waals interface, we can now combine any material, and there's a little bit more. So here, if we have 2 materials, we can rotate them. And now if you look on this, during this rotation, you see there's a different pattern form depending on the rotation angle. And of course, also a little bit on the lattice constant. So, but if we have the same lattice symmetry, which is given by the 2D materials, it's hexagonally, most of them or a lot of them, we get a hexagonally superimposed pattern. It's called Marie pattern, maybe also from digital photography. And this Marie pattern can generate a lot of effects. So first of all, let's first see if it's true. Yes, it's true, because it has been proven if you combine hexagonal boron nitride and graphite and do the topography scanning microscopy image, you see very well this Marie pattern. So that's not this hexagonal structure of the individual lattices. The scale by 10 nanometers, it's really the Marie pattern. And now with that, there are 2, let's say, directions when geometric effects in real space do this, let's say, Marie pattern, and one is on case-back effects where the band structures influenced. So for the geometrical effect in real space, due to the different registries, if you go to these different sides of this Marie potential, where different atoms are lying on top of each other, you get a Marie potential landscape, also in the single particle energies. And it looks like this, where you have this kind of, quantum confinement, like little puddles holes, where we have discrete states, and these discrete states can be seen like quantum dots, where excitons can be confined, and that's a measurement energy versus excitation power. And you can see on the left hand side, first just a few excitons are filled in, those are again like single photon emitters, and then you can set it more and more and more, such that you can really fill up this Marie potential with excitons. And another direction, the K-space effects, is such that you can see again this lattice has a high periodicity. And if you go back to your textbook knowledge, what happens if you have a periodic lattice? You do the Bloch ansatz, you have a periodic part in your wave function, and you do the Fourier transform, you go to K-space, and everything can also be done here. So meaning you can also do the same for this Marie potential with this long wavelengths. With that you get a so-called mini Brillouin zone, superimposed to the large one. And with that you get an energetics here as a function of the twist angle, because with the twist angle you can adjust the length, the wavelengths, the lattice constant, so to say, of this Marie potential. And with that you dramatically change, let's say, the energetics, and the color code here is the density of state, which is plotted again here, energy versus density of state. And you see that's graphene, so that's the Dirac, let's say, part. And here in the middle, something new happens. You have this huge flat bands with a high density of state. And now if you tune the firm energy in a field effect structure through the state, you can see about the properties. And this is a very rich physics which is coming into play. So here is plotted the temperature versus the density, so meaning the position of the Fermi energy, and the resistance is color coded. So you see you have some domes where we have superconductivity, we have regions where we have an insulating phase and some regions in between. And now let's briefly think about what's going on. So here we have the so-called, in the outside here and here we have the so-called band insulator. So meaning here there's just no allowed states, and instead it's an insulator as we know it from a normal insulator, from a semiconductor, if the firm level is in between. And then as soon as we cross this flat band region from here to here, we have this interplay of correlated and superconducting states. And where does it come from? So actually, rather briefly, it comes from strong correlations from an interplay of on-site potential and kinetic energy. It goes back to the so-called Hubbard model. So meaning it's difficult to describe these strongly correlated, let's say, systems, because we have a lot of large systems with strong correlations, which is really hard to describe theoretically. And here Hubbard defined somehow a model where he said, well, we calculate on a lattice. So we have just two energy sides. We have the hopping term, the kinetic energy, and the on-site potential. So meaning on-site potential means if there's already a state at one side, you need to pay an energy penalty to bring in another state. And it must have opposite spin, for instance. And the interplay of the hopping term and the kinetic energy term is very crucial to define the properties. So in general, you would need, let's say, a rather low kinetic energy, let's say, and high onset potential. A flat band is exactly where we have low kinetic energy, but then high density of state. And we said this correlated phenomena can occur. And now, this is a theoretical concept, but it's hard to prove it experimentally. And now with this phenomenon of having this twist degree of freedom, it can be proven, because now we have exactly those lattice sites. And then you can play with the Fermi energy to say, well, we have just every second side is filled. And if every second side is filled and every other second side is half filled, it already means that they have some attractive potential, because here this side would like to have another state. This has one. With that, it's like an exciton, like an Elton hole pair, which can bind. And with that, you can drive these phase transitions if then the interaction between a different side is strong enough. And with that, we have here, first of all, a system which can give us this emergent phenomena and correlated behavior, highly tunable. And on the other side, we can also prove this theoretical concept, which is quite nice in terms of this Hubbard physics. With that, I'm at the end. I would like to thank, or like to wrap up. So meaning we talked about what is an quantum material. We talked about emergent behavior, importance of interactions. We talked about 2D materials, why they are so prominent, because they're highly tunable, universally integratable, and interactions in particular can be tuned. And we can use them for generic quantum effects like the single photon emitters, but we can also use them by twisting and stacking as a Mortabat simulator and to really go to the interesting correlation physics, which can also result to some applications. With that, I would like to close here with an impression of the labs, and thank you very much for listening. And now I'm happy to take questions.
Thank you very much for very inspiring presentation. And I would like to welcome the attendees to raise their hand or ask question in the chat box if they have. It was a very interesting presentation for me as well. So while waiting for the questions, I would also like to ask some details as I have a chance. You mentioned that you can place these very thin materials on pillars and get some light emission. And I was wondering, is there any importance if these pillars are arranged at some periodical distances, or just the shape was important there?
Well, actually, it's really the shape. So meaning, of course, you can think about if you then have these emitter sites, you would like to couple them by dipolar interaction, for instance. Of course, then it should come close. But no, otherwise not. And here, of course, I did not, maybe tell the full truth. So with the pillars, if you go down really to the nanometer scale, the pillars you can create by nanofabrication typically have, still, they are not pillar-like, they're little like dome-like. So meaning the strain potential is not at the aperture, most likely it's at the side where you get some folds. You can think about like a tissue which you take up and where you get some folds. Okay. So that's a little bit, there are some limitations, what might be some technological, let's say, solutions to that, but to precisely define the strain on the atomistic scale is difficult. Okay, thank you. I still don't see any questions. So I would like to ask another one that I was interested in. You showed that you can apply these thin materials between two layers and get some interference and reflectance effects. So I was wondering, has anyone tried, or your group tried, to do some device on purpose, or it was just investigation of how these materials look like in such a way? First of all, I guess it was the starting point for the great success of graphene, because the proper substrate was used. So meaning the Manchester group used silicon and silicon dioxide with exactly 300 nanometer. And if you look for the interference contrast, if you would use 200 nanometers, graphene is invisible. You can really check it. I guess, that's the first application to say, well, use the proper substrate, for each material. It depends on the, refractive indices of the individual materials. It can be calculated. It's not that hard. So we're doing it in lab classes. So meaning, I guess that's the first application to just identify the materials, but there's more to it, because it of course also depends how much light you can get out of a system. So meaning, if for any optical measurements you would like to do, and also should consider about this interference effect, which has strong dispersions. So meaning it depends on the energy of the light. So meaning, just by saying, okay, I excite with a blue laser or with a red laser, doesn't mean if the power meter does tell you the same light fluence or the fluence of the laser, it doesn't mean that the same, intensity is really seen by the 2D crystal. Okay. But, something which needs to be considered as well. And of course, it can be used for applications if you would like to enhance emission or absorption properties. Okay, thank you. There were so many applications mentioned that I guess that most of the listeners got excited and might change their research field now to 2D materials.
or invite the elephants in the backyard. As I don't see more questions, I would like to thank very much for joining this student conference. And yeah, if you are interested, please stay for further presentations. And with that, we are probably going for a short break. Thank you very much.
Okay, thank you very much. And no.